I intentionally did not send a title because I was not sure what to present. We do so many things in these directions experimentally that I decided to present both. So I will present a little bit in the direction of quantum networks, and when I say quantum networks, I mean networks we deploy either in the field or in the laboratory, and then I will also describe a little bit about our experiment together with the Chinese Academy of Sciences. And last but not least, I will compare these two experiments with each other. There are very recent publications in these directions, how to compare that, and I have to admit that I'm not at all a quantum repeater expert, so I really don't understand the assumptions which go into these repeater networks. But nevertheless, we will manage together to de-scope this thing. So yes, so you all know, and I will go through very quickly because I have too many slides in my presentation and I don't know how to delete these. But you all know that there were a lot of trusted node implementations. The one in Vienna in 2009, the one in Tokyo in 2011, and then just recently, people in China started the same thing in the sense that it is a trusted node network, and what you see here is just the backbone. This was realized already a couple of years ago, and each of these lines, at each of these 32 trusted nodes along this line, the network spans out in both directions. So the number of nodes they have now available, not even the first couple of authors of these publications know. They said it is in the order of a couple of hundreds of nodes already. So this is the state-of-the-art technology, and you all know the pros and cons about trusted and untrusted thing. So the data rate of this is a couple of kilohertz, thank you, and it scales very nicely with distance because it is trusted. All this hardware is produced by a company in China, and none is coming from outside China, although I heard they tried very hard to buy it outside China. But this is not, there is no manufacturer who can really deliver a huge number of devices in a short period of time. We were thinking of how to implement these networks a little nicer, and what was in the literature before we started our effort in quantum networks was, for example, that based on an entangled photon source, they used optical switches, 1 to 8 optical switches, so they could deploy entanglement between one of those lines and one of those lines at a push button. But so they could connect, for example, that user with that user, but obviously if you want to connect one user with the other user on the same side, this is not possible. So the dream of all networks, and the backbone, the real backbone in the classical internet is what is called a fully connected network, where everyone can talk to everyone else. Please remember that in the classical network, this is the case for a different reason, because they do active routing of data packages. This is not because of connecting everyone with everyone else. It would require that you at home have the equivalent number of fiber optical cable going to your home than the number of users in the internet. This is obviously not true. And if you do that in a quantum internet, that would very badly scale. So we invented something else, and when I say we, I mean my former postdoc. He thought about Siddharth Joshi thought about how to use an entangled photon source and cut out the entangled spectra with the use of this WDM. Forget about this. D is just dense wavelength division multiplexing. So you combine all those colors in one strand of a cable, and then you demultiplex them in color, a very standard technique in classical comms. And you can do that in a Sagnac interferometer style type 2 zero source as well, where you use the two correlated colors. If you select the wavelength to be measured, you can measure the polarization in the right way. And the real expert in this is Søren Wegerowski. He is in the audience, so he really knows how to do this. You have to know if you produce with the type 0 spectrum of your down conversion, if you pump it with the center, the half of the wavelength of the center wavelength, then you know that the two red ones are correlated with each other, the two green ones, the two blue ones, and so on. This is called the I2 grid. So this is the grid the classical internet people are using, and you can select these two colors to match. And he was able to find the right colors who are correlated with each other. This is a funny pointer here. And then you can easily see that if you select the right colors here, you can see a very high degree of entanglement. And you can do that at any correlation. And if you use these 12 WDM channels and combine them in a clever way to 4 users, then the 4 users see 3 different colors, and that cable goes then from the quantum network provider to the users in the end. So you can think of this device here, this region is the network provider there, so there is one source, one deployment of entanglement in colors, and then you have one only and one cable to the end user. And then this funny distribution of colors, and this is what Sid invented, allows you to communicate to everyone else just by using the entanglement, and there is no need to deploy like six cables. It's just 4 cables. Everyone is connected to a center source. And this is very similar to a classical situation. So if you buy an internet connection at your home, there is no need to buy hundreds of thousands of cables. You get one cable at home, and then something at the internet service provider has to be changed in order that the packages are routed to your house. So it's very similar here. You get one cable to your home. This is the single mode fiber cable getting to your home. And then something has to be changed, obviously, with the colors here on the network service provider position. And these links can be long. So it's only one link connecting the fibers. So this is the source Søren was building. This is a 775 laser which pumps this Sagnac style entangled photon source, and the 2 photons come out here in these 2 colors. And this is what we call our fiber salad. So this is the combination of all these WDMs, and you splice them together. And really only Søren knows how this really works. This looks awkward, is awkward, but it will get a bit worse in the next couple of slides. So this is the receiver optics, and you see here the correlations in time. So every combination of users have their own timing offset, and you see here the amount of coincidences between the different users. And that is a very nice way to distribute entanglement among 4 users, a very simple, scalable way, and we published it just recently, half a year ago in Nature. This is what we realized at that time. So again, on the physical level, you have a connection from the service provider to the users, and on the quantum level, you have entanglement between all of them. And you want to expand that, obviously, to a larger group of customers. So we want to go bigger and bigger and bigger, and this is not what a small country like Austria can do. So we went to the UK because they have a lot of detectors in Bristol. This is one reason, and also the key personnel changed their job. So we sent our source and our people to Bristol, and they come up with another idea, and this scale is a bit different. So the 2 photons come out of the source, and you split them with a beam splitter randomly into 2 subnets. So the 2 photons go either this way or this way, and then they are split up in the traditional way with the help of this division multiplexing system, such that the 2 photons either being split up here or being split up here, or if they go to the 2 networks, they're splitting up here or down here. So this is the 2 correlated channels we sign here with the numbers. You can see that everyone gets an entangled photon pair with everyone else, apart from little connections which I will talk about later. So one connection is this. This is what the upper side is producing, A, B, C, D, and then the lower one is the red one, H, G, F, E. Here, and then you add the connections, the outside connections, with the help of another beam splitters and wavelength division multiplexers. So there are some links which have double connections and one link which has single connections. They are preferred users. This looks pretty complex, and I have to admit it takes a long time to understand that. But if you go through, it's really geniusly simply invented. But if you build these things, it gets so complex that you would not believe. And this is the fiber salad Søren and Ceylan was building in Bristol. You have here the polarization compensators. All of them are polarization compensators. You have to compensate like 32 links between the colors, and the wavelength division multiplexers are in these books. So these are literally books where you have all the wavelength division multiplexing things. So this is really a very impressive machine in the end. I mean, you can scale things up on the chip, and you can make this much better, much nicer. But you know, we are experimental physics people, and we are just interested to do the first experiment, not the best experiment. We wanted to scale up a little bit in the sense that we did not want to use one single detector at the receiver, but we could not afford to do a fully fledged QKD protocol with 4 detectors for one user. So we did an intermediate step, and together with our friends from Croatia, they built receiver modules where we analyzed the polarization of the photons with the help of 2 detectors only, not 1, not 4, a compromise being 2. So one mutual unbiased basis state is measured immediately, and the other one is switched by the half-wave degree, the 45-degree basis, such that you have a little offset. So by the timing, you can see the photons, and you see this huge number of detectors, and you can imagine how much that costs. And this is was done, purchased in Bristol. So this is the full setup. This is the one setup, as I explained. This is the second setup, as I explained, with all 8 users, and then with the full complexity of all the additional links, beam splitters and wavelength division multiplexers. So it's really a lot of setup, and I have to also say it takes a long time to adjust all these polarizations. You have to really make them indistinguishable from which color it really comes to the detector. So this is our official naming table here. I don't know if this will hold in history, but you know, there's even a Chinese girl here, so we try to make this really international, and also an Austrian, you know. So we realized 8 users with that, and people were bold also to go out into the field. So we used long fiber cables which are deployed in Bristol from the university to distances like 15, 16 kilometers, and attenuations per link in the range between a few dB minus a few dB to like, I don't know, 12 or 15 dB. So this was the attenuations, and with that still we could see entanglement, and we distilled a secret key out of that with the help of a software we wrote, or Leo Bo wrote, a fully fledged quantum key distribution experiment based on entanglement with 8 users in a deployed field situation. So as you can see, it's also the analysis of that data is not so easy anymore. You have a lot of twofold coincidences and polarization, and the secret key rates of all these combinations you can see here. And the deployed fiber salad was stable to up to 7 hours, and this gives you a rough feeling of what a manual setup is able to do. 7 hours is quite a lot already. So if you want to go to a fully operational setup, you have to do some self-alignment procedures. You have to align the polarization or the timing or whatever you use as a degree of freedom in your QKD system. But this is what the passive system in the deployed fiber is providing you. So this is the team. As I said, Søren is here. Neumann is also from Vienna. These two are from Croatia. Sid is a former Austrian postdoc, and Jalen, who really did the experiment in Bristol. So what the future will bring is something I will quickly display here only. It's not very usual to speak about the future in physics experiments, but I do. So deep investigations using Google Maps, I found out that Vienna has a very fortunate place in the world, such that the capital cities are very, very close to each other. This was a new discovery for me. So the distance to Bratislava is only 70 kilometers, and this is 200 something kilometers to Budapest. Ljubljana is a bit further already, and these are distances contemporary QKD systems can easily breach. And when I say easily, I talk about a secret key rate, in a realistic secret key rate of a couple of hertz already, which is useful for some applications. There is one region in the world where the capital cities are closer than here, which is Vatican and Rome, but this is already boringly short. So we decided to stay in Vienna. It's actually the first experiment we do in Vienna on a long distance site. So we talked about to many service providers of fibers, and no one in Austria was able to provide fibers because this is science, and we are not able to pay the full price. The full commercial price is about €7 per kilometer a month. So you could not afford to do something like that. We talked about Telekom Austria, which is half Mexican, half Austrian company from an official post office in Austria, but they really said no at the end, and the only sponsor we could find is Türk Telekom. And this gives you a glimpse of understanding where the modern science is going. They are very happy. They are very happy to help us. They made a very good price. It's not zero, but the price is doable. And we got a lot of links between Budapest, almost all the way to Bratislava, and then also from Bratislava to Munich. That link already is established, as you can imagine, to Turkey. And also to the north, we are now discussing with the Czech people from Poland. So the first links we will use are the links between Linz, Vienna, and Bratislava, and further on this going to Budapest. And this is a distance of a couple of hundreds of kilometers already. This is now the first experiment we are implementing in the next couple of weeks. So we got the lab ready in St. Pölten and in Bratislava, and this is what will be done. And the secret key rates we expect there are in the order of a couple of hertz. So Vienna, having the source in Vienna and the one receiver in Bratislava is already kilohertz. And if you have the source in Vienna and one being in, having the source in Bratislava, the receiver being in Vienna and Budapest, you get about 1 hertz. So this is pretty much what you can do with contemporary systems. So in the next part of my talk, I will present our experiment we did together with the Chinese Academy of Sciences. You all know how to do a trusted node quantum relay with the help of a satellite. So you do one key with the satellite to one ground station, a second key with a second ground station, and then the satellite compares these two keys and tells one ground station which bit to flip. And in that way, these two ground stations share a quantum key, although they have never seen each other. This is what we call a trusted node on a satellite, because you have to trust the satellite for that protocol. The satellite itself was... Yes, this is different from using entanglement, where you don't need to trust the satellite. So the picture is a bit unfortunate. So we did this really from Austria to China. So this is 7,000 kilometers. You won't see the satellite at all. So these are two different downlinks, two different decoy BB84 downlinks from the satellite. The satellite is a Chinese satellite. The satellite was built, the frozen specs was in 2010, 2011, so it's almost 10 years old, that machine. So this used the know-how we all had on the scientific market from 2009, 2010. Just keep that in your mind. And the satellite was equipped with a decoy state protocol source at 850 a nanometer, and with a repetition rate of 100 megahertz. They had a beacon and a synchronization laser. So this is a green laser which emits the timing reference to the ground stations. At green, this is a very strong laser. You will see in a second. And it has also an entangled photon state on the satellite, a source on the satellite. So one telescope you see here, it's 13 centimeter, and the second telescope is here, it's 30 centimeter, and this is also a receiver, so you can also send photons from the ground to the spacecraft. So it's a Sun-Synchronous Orbit. The orbit is designed such that it has 97-degree inclination, so it means that at midnight it always is above Beijing. So this is the largest ground station they have, close to a city. The height is about 500 kilometers. At every midnight the satellite is in Beijing. This is not true for all latitudes, obviously. So for Austria it's plus minus 2 or 3 hours. But that's it. So for the 500 kilometers, you have a link duration of about 300 seconds. So you see the satellite from one horizon to the other horizon for about 300 seconds only. we did a few links to and from the ground station. So we had a lot of trial links, and the ground station in Austria is actually in Graz, where there is a very established technology. We later did also an experiment on Tenerife, but I won't speak about that because this is not published for whatever reasons yet, but we published already together with the Chinese the Graz experiment. We never tried to use the experiment in the telescope in Vienna because the platform is very unstable and is not made for that, but the telescope in Graz is especially built for that. So this is a 50 centimeter Cassegrain configuration. You see here in green, which is later switched to red, so it should be a red laser here. We emit to the satellite a very strong laser, which is a couple of watts with a divergence such that it illuminates the full orbit uncertainty where the satellite might be, because these two-line objects you get from laser ranging are not very precise. You know, the satellites, they wobble around this very complex gravitational field of the Earth, so the predictability is very small, so to the extent of a couple of 100 meters. But with the help of these lasers, you tell the satellite very precisely where we are. And this is the quantum payload. So you get the photons, the single photons go into the main receiver. There's the primary mirror, and then this is the secondary mirror, and it comes out here. And you see here the 4 detectors. This is the beam splitter, the polarizing beam splitters here, the time-taking unit, and the computer. So this is the full experimental setup we had on the ground. We got the timing with an additional pin diode from the green laser use. So this is the full setup in Austria. So once again, you have the fine pointing camera, you have the timing in green, and you get the single photons to your receiver side. And then the satellite comes above the horizon, so we approximately know where the satellite is. We illuminate the full portion on very close to the horizon, so we could start already at a very low elevation of 0 to 5 degrees, and then we capture the satellite just with a couple of hundreds of milliseconds in the end. And the satellite then answers back with green light. So this is the launch of the satellite in August 2016. Then I have to say that the Chinese did starting to do the experiments in December. They published around Easter the first science papers with 2L downlinks and so on. So even the commissioning phase of a satellite in China takes a couple of weeks. In Europe and the US, it takes years to provide a scientific instrument in orbit to the science community. We will not look at that. This is just a funny video of the launch. So this is a multi-photon multi-photo picture we took for the downlink from China. So this is a normal airplane. You see here Earth moving, so these are the stars. The satellite, we send here red light to the satellite, and then immediately the satellite answers with green light. And the green light is very, very, very bright. So this is almost a religious experience if you stand on the parking lot and you see this bright light from sky. And if you go like 5-10 meters away, you see nothing anymore. So the satellite is very, very well focused, just limited by the divergence of the sending telescope and the atmosphere a little bit. So this now gives you a little bit of an understanding what happens when the satellite passes over. So this is a bit. The orbit needs about 300 seconds. So this is done at higher speed. But you see. Okay, now I make the joke because the Chinese The Chinese use a very different sound, and then we decided. So coming back to the science, this is the elevation of MOTSI. This is the official name of the satellite. The satellite is here not going through zenith, because a telescope cannot point to the zenith very precisely, because it would have to turn arbitrarily fast. So any telescope has a singularity somewhere, and the azimuth Atzmont has the singularity in the zenith. So we could use about 82, 83 degrees in the zenith as the satellite. So this is where we have the shortest distance, about 500 kilometers, and this is where the satellite is about 2,000 kilometers away. And then you see here, this is the tracking performance of the telescope. So if we mispoint, we don't the single photons anymore on the single photon detectors. The spots have a diameter of 120 micrometer approximately here. So if we are tracking the spot is very well centered on the detectors, but if we switch off the beacon by just blocking the cameras and so on, you immediately see that the telescope goes away. So the satellite path is really very complex, and the precision we can do these kind of things are arbitrarily are very good. But I have to say that this is a very, very standard technology, because laser ranging techniques are using this from the 60s already, 70s already. So we know very precisely where the satellites are because of satellite ranging. And this is also a single photon business, so it's very similar, and we used that a lot during this experiment, that know-how which is available in Graz for the pointing and the tracking. So you see here that the polarization contrast is very nice. You really have, if they send only one polarization, you really have only one polarization and the other one not on the detector. So they switch the polarization also during the orbit. So then I couldn't find the right graph. So we really had both polarizations on our detectors. So this is a typical flyover of the satellite. You first see the beacon laser. So this is the sync laser. The sync laser gives the timing when you expect the photons, and then you see to like 60,000 counts the photons, the single photons coming from the satellite. So this is around zenith orbit. And you can easily see here that at large distances of 1,000 kilometers, we already have a shifted key of 2.5 kilohertz. And we had problems with Q-bar going up a little bit, so the key rate does not increase so much anymore with lower distances. But this is approximately what we could do in that experiment. So here again, in that publication, we showed two experiments. Together with the Chinese, we showed two experiments. One is deploying a key over 2,500 kilometers, and the other one over 7,600 kilometers between Beijing and Graz. So the final key rate of that system is here. So one has to say here, I would not say it in a larger room, but here we are among each other. You have to see that these numbers, the final key rate, Mitzius Graz, are a little bit higher than the final key rates in China. Although our satellite, our telescope is much smaller, just 50 centimeters, and they use up to 1.5 meters in this experiment. So nobody knows why, but the performance in Austria is quite good. So this is the crowd of people who did the experiment. This is Liu Bo. He's our software programmer, and without him this would not be possible, because the real classical communication in this quantum key distribution system was WeChat, run by him, and he really literally talked to you know, the guy in the operation center in Beijing, and we could really understand what's going on and what they do next and so on. So based on official information, this would not be possible. But if you have a good classical communication with which it is possible. So this is now almost my last slide, and I would like to share that with you. It is somehow a bit new to me. It is not a slide I made, it is a slide Hugo Spinton made from University of Geneva. This is Hugo Spinton's hand. And it is not published anywhere, but a very similar publication was done by Christoph Simon and Thomas Jennewijn's group in Canada. And they were trying to compare what's going on in fiber and on satellite on the market currently. And at least to me, this was a little eye-opening, and I don't fully understand it, and I don't understand the assumptions which are going here. But let's go through. So the first column is providing entanglement with the help of a fiber with quantum repeaters. The quantum repeaters, they run 24 hours, they run all year, and they according to Hugo's simulations and assumptions and best understanding of future technology, so it is not available today, they will have a final key rate of about 0.005 hertz. And the cost, he estimates, for one of these links over 1,000 kilometers is in the order of 10 to 20 million euros. So this is future technology. This is something they put a lot of money into, and this is what they do right now and what they believe they can reach in the future. So now we are talking about a satellite which is almost 10 years old. The satellite has about 300 seconds flyover every day, which is very pessimistic because we have some nights with 3 links, but let's assume it's only 1 link. It is weather dependent. We can only do the experiment, and I forgot to say that, when the satellite is in the core shadow of the Earth, so not when the satellite is in the sun, because you look with your single photon detectors with a giant collection machine to the satellite. The situation is not so bad. You still don't saturate your detectors, but you cannot do QKD, a standard QKD at that point in time, at least. So you can only do it when it is in the core Earth shadow, and on 24 hours average, it yields a secret key rate which is the same as the future quantum repeater system would do. This is available today, and to the cost of, he says, 200 million euros. So we are talking about a very long link. I was briefly talking to Hugo. This is pretty much limited per color, so they also imagine to use WDM systems. WDM systems, you can do like 100 in parallel. This is the only way to speed up a quantum repeater-based entanglement distribution. You can also use a lot of fibers next to each other, but all of these can also be done with a satellite at the same time. So at least for me, it was somehow interesting that it is with a 10 years old satellite technology, you can reach the same key rate as you use with a future QKD-based system. And that number is optimistic, and he believes it cannot be improved by a lot anymore, because it's already given by the coherence length of the photons. You have to couple to atomic devices and so on and so forth. The other ones are trusted repeater devices, so it's the same as the Chinese do right now. So this is what what Hugo believes. This is the final key rate, or the current state of the art system would deliver, and also what the satellite, the XOR situation, as we depicted here, is the same thing. So what is clearly missing here, and I have not enough resources, but I'm really looking forward to someone who do a trade-off of that system. So at which point, at which distance a satellite is already better than a fiber-based system. So at which distance it would not make any sense anymore to use a fiber, but a satellite. If you would ask me, that costs is very, it's underestimating the cost, because this is only the cost between 2 points, A and B, with 1,000-kilometer distance. If you want a different situation, you have to invest the same amount of money. A satellite can do any point in time on ground, any combination of points on ground. If you use a satellite in the order of 1,500, 1,600 kilometers, so this is the optimal case, then the distribution of entanglement is already in the order of 5,000 kilometers, and you would be able to connect London with New York. With a situation like that, you would never be able to do that. And I believe that after a couple of hundred kilometers, you would already use a satellite rather than a fiber-based system. But as I said, I haven't made the calculations. There's surely something you have to do to maximize that and optimize that and see for the real trade-off. So if one of you are interested into that, talk to Hugo and to Simon, Christoph, what needs to be done here. So last but not least, but this is for me the most important slide, I'm heavily looking for postdocs and PhD students. If you know anyone who is good looking as Søren, then please tell us. We are hiring right now. Thank you very much.
Thank you very much.
So your repeater numbers at 0.005 hertz, I think, is a very old conservative system, conservative numbers. I mean, what is this, 5 millihertz or something?
Yes.
That's very, very conservative these days. The new generation of repeater schemes that people are talking about, even the second generation, will take you up to the kilohertz rates if you have good enough equipment. So basically,
yes,
it's a moving game. This is, I would say,
but you're talking now a quantum repeater with an input and the output in the lab, and there it's a kilohertz. So the device itself costs photons, right? So you have loss in the quantum repeater because they are limited in linear optics and so on, and also loss in the components. So what you talk about, the kilohertz, is really the input of the machine, the output of the machine. But here, in 1,000 kilometers distance, you have to break it up in like 5, 6, 8, and then you have to optimize things. Assume that the repeater is arbitrarily good, fidelity of 1 and storage time of an hour or a year, and cost of 0. Then you implement quantum repeaters along the line. And this all costs photons, and also the line between the repeaters costs photons. So, you know?
I know, I mean, I'll disagree with you, because people have done the calculations in real telecom fiber, and maybe they're not a kilohertz, but they're definitely not 1 millihertz.
Yes, but not at this distance, to my knowledge. All the simulations I know are locally input and output from these quantum repeaters. But there is no optimization of long real links. I mean, if you could point me to these publications, I would be very happy. But to our understanding, this is not available.
All right.
You mentioned that the satellite is quite old and there's room for improvement. Which are the key things you could go to improve the quantum links? Is it the wavelengths or what?
So the satellite is using a decoy source with 100 megahertz. If you ask some 5G people to build a 10 gigahertz source, this is doable with present state of technology. So this is a factor of 20. Who says that you only communicate with the ground station at one wavelength and not with like 100 wavelengths? Who says that the satellite only has one telescope where you point to one ground station? Who says that the satellite has to have 2 telescopes? Why not to build a satellite with 20 telescopes? This multi-array antennas, as in an RF, all of this is done. And in entangled photon sources, the satellite Mitzius has an entangled photon source with a repetition rate of about 1 million. And this is definitely not the end. I mean, we know in the lab now how to build like 10 million and maybe 100 million. This is the scientific market. If you do that and then if you add up these numbers, you really reach a couple of kilohertz. And then you also want to optimize distances. So you want to be very close to the customer because you want a short link because of the divergence, which is the main loss mechanism. But then the link duration is very short, just a couple of hundreds of seconds. So you want to be very high, but then, the divergence. And the optimum seems to be in the order of 1,400, 2,000 kilometers, which is a very, very expensive orbit. So that is expensive because OneWeb is buying all the launchers for the next 10 years in that. So people are now thinking to go to a geo orbit with future technology. And when I say future technology, meaning that ESA believes they can build like 0.5 meter telescopes on the satellite and 2 meter telescopes on ground for a competitive price tag, then you would end up with a hertz on ground. And the satellite would see the full hemisphere, so you could talk from Sweden to South Africa. So these are the trade-offs on the market right now. But I try to emphasize that what the Chinese did is a very old technology, and if we cleverly think about future technologies, then we can improve a lot. By the way, the Chinese had half a second mission in space already on Tiangong-2. It's a telecom wavelength decoy system. And there the repetition rate is very high because they use standard components from telecommunication industry. It was launched also in 2016. So the Chinese launched 2 missions within 6 weeks. And we Europeans couldn't launch anything within 15 years into space. I had to say this sentence.
All right.
Yeah, maybe it's not even older, but the frozen specs is, I think, 2011. Yeah, exactly. Yeah.
Okay. So just on your fiber-based network, is this fully multiplexed in the sense that sort of all pairs of users can communicate at the same time and you can arbitrarily choose which of the pairs, or is it just one pair all?
I know there's sometimes the misunderstanding that we distribute multi-photon entanglement, so this is not. At the end of the day, we distribute photon pairs to everyone, statistically to everyone, so everyone shares a memory of the keys, but it is a 2-photon system. It is just routed by the colors. So it's at the end of the day, everyone is able to talk to everyone else. So it's not a multi-photon experiment, it's still 2-photon. This is why the rate is pretty high, not very high, but pretty high.